let's get started. So before we start, we learned last time the three ways of solving a problem. First one was whereby there is exact perfect equation that fits into data points. We can figure that out easily. The second way of solving problem was by doing the approximation. And how did we do that? By doing the mean squared error, by using the normal equation. That was the second way. And how did we derive the normal equation? We basically, for a particular line with some slope and interception, or like theta 0 and theta 1, we computed the error, and then we differentiated this error with respect to the theta 0 and theta 1, and equated it to 0. And from there, we computed the theta 0 and theta 1. That's normal equation. In normal equation, we equate the different derivative of the error to the 0, okay, with respect to each of them. Then the normal equation is not great when there are features, when the number of features is high. Before this, we have done the two big end-to-end project. One was regression and other was the classification. That must have given you an understanding of what's going on, how to get the project done, how to build something end to end. All right. So as of now, you will be, in the shape to get started with most of the projects. And in most of the projects, you will become very, very comfortable in solving or predicting based on what we learned so far. Right now, what we want to learn is we want to learn what is going on underneath. Okay, what is going on underneath under these prediction algorithms, and we will start with the foundation of most of the machine learning, and that is gradient descent. All right, so we what we learned last week is that the notations, M is called the number of instances, meaning the number of rows, and N represents the features, M for instances, and the notations. The note with respect to each row or each instance, we call it xi. Okay, yi represents the label and x suffix I. All right, and then if you combine all the x's together by transforming it, by making them horizontal from vertical, then that becomes our whole matrix, the capital X, right? Y hat is y hat represents the prediction at any point of time, and the objective is to find the prediction which gives the minimum error. The RMSE, or mean square error, is the usual cost function. Then we talked about linear regression. Essentially, if you are given the data, all we have to do is find out that line that goes through that data. If this data was all in a straight line, then we were in luck. We could just solve this the equation with two data points, and that would fit everywhere. So, but that's not the case in most of the in most of the regression problems, that they don't fit, all the data points won't fit into a straight line. Most of the problems are approximation. All right, so here theta 0 and theta 1 is what we have to find out. That's the objective of the machine learning here in this case, that find those theta zeros and theta 1s such that life such that we can predict the life satisfaction given GDP per capita. Right, when we say machine learning model is nothing but collection of theta zeros and theta 1s. All right, now that's the linear regression. So there are multiple ways to do it. One is we can just write an infinite loop, or we can just write like really huge number of iterations that try all possible slopes and try moving the line for the same slope at least 500 times, right? So we could try like every angle, and for every angle we could try all possibilities, but that's just too much, right? That's just too much. So it's better to have some other optimization, correct? The other optimization could be that we basically, for some theta 0 and theta 1s, we take the line, we take the line and compute the error in terms of algebraic theta 0 and theta 1, and differentiate the error with respect to these. Or what we can do is we plot that error, on graph with respect to theta 0 and theta 1, correct? And then we figure out that, okay, for theta 0, this is the point where the error is minimum, and for theta 1, this is the point that where the error is minimum, right? That could be another way, but that'll be, for this kind of data, we have to just find the line that goes through these such that the error is minimum, right? One of them could be just do a infinite iteration, and the other one could be that we can compute the error in terms of theta 0 and theta 1. We differentiate the error with respect to theta 0 and with respect to theta 1 and get the answer, right? This technique is called normal equation. All right, we have gone through this. So find theta 0 and theta 1s or the model such that the error is minimum by the way of differentiating and putting that to 0, correct? So the biggest use of differentiation, one of the biggest use of differentiation is in terms of optimization, that given an equation, if you want to find out the minimum or maximum, you could use the differentiation in order to find the minimum or maximum. We can differentiate it with respect to 0. The point at which the slope is 0, you will find the maxima or minima. All right. So that's the role of differentiation. Those who are trying to see the detailed approach of what I'm explaining, you can also take a look at this URL. This is from the Wikipedia. I really like this explanation. And so this is what here is being done. Specifically, what is good is this example, right? So this is the data points. These are the data points. So one is we could come up with a new line, B1, B2, and we have these 4 lines, right? Now the error that you see with respect to this line and data points is basically this is the line, these the errors, right? This is first error, 6 minus beta 1 plus the this one, right? And this is the error, and then this is the error, right? And then this is the error, and then this is the error. So we have summed up all the errors, right? For x equals 1, for x equals 2, for x equals 3, for x equals 4, and for x equal and so for these values we have computed the error here, right? That you see. Okay, these are the data points that are given to us. Okay, these points are given to us. That's our training data. Using that, we estimated that our model will be something like this, and we said that okay, it's going to have beta 1 and beta 2 as the model parameters, right? We call them model parameters or thetas. Now here, this is the error. Now, after you do all the summations, we'll get some expression like this, right? You see this? This is some expression. And afterwards, when you want to find out those values of beta 1 and beta 2, where this error is 0, right? So what you do is you differentiate this with respect to beta 1, and you differentiate this with respect to beta 2, and equate it to 0, right? And that's where you see these, you'll get 2 equations. So when you differentiate it with beta 1, they'll become 8 beta 1 and so on. And these when we are differentiating with respect to beta 1, we consider the beta 2 to be constant. So beta 2, these parts are gone. Similarly, when we are differentiating with respect to beta 2, then first part beta 1 is, this one is gone, you're left with this, all right? and so on. And then once we get this kind of expression, the two expressions, we can just eliminate, use our normal variable elimination, and we'll get beta 1 and beta 2, right? Now, you might be wondering that what happens if there are more than two betas here. Let's say we are doing it in 3 dimension, therefore there will be beta 1, beta 2, beta 3, or theta 1, theta 2, theta 3. That's the way we have learned. Now, if you have three variables, there will be three equations, because first you will differentiate with respect to beta 1, beta 2, beta 3. And then those three equations we can solve. Now, the challenge with this one is, here we were doing the straight line. What if we were trying to fit in a curve? Then solving these equations will not be linear. They will be complex equations. Therefore, this approach does not help much. Also, if you have more thetas, you see, more thetas, there will be more number of equations. Solving more number of equations takes a long time, right? The number of, if the number of equations are just too many, it takes a long time to solve those. Okay, so in the quadratic equation, it could become really complex afterwards, right? And though it looks simple here, but if the equation is a little bit more complex, whereby beta 1 is squared plus c and so on, that become really complex, and hence the normal equation may not be very useful. All right. A question from Bo is that how is matrix optimization part related to partial derivative minimization? Very good question. Thank you, Bo, for this. Now, if you see here, these are these are consecutive equations that you'll see, correct? When you want to solve, when you want to find out or solve these how do you generally solve such equation? 8 beta 1 plus 20 beta 2 minus 256 equals 0. 20 beta 1 plus 60 beta 2 minus 154 equals 0. So what will you do? You'll multiply this by 3, eliminate this and this, right? And it'll be 24 and 20. There'll be 4 beta 1s and so on. And then we'll find out the beta 1s, correct? By eliminating first beta 2 and then eliminating beta 1. All right. Is this analogy clear to everyone? The one that I walked you through, this linear least squares way. Okay. Feel free. I mean, this is important because the soul of entire machine learning is basically the the, the, these kind of approaches. Okay, these kind of approaches is what help you think about machine learning in a broader perspective. Otherwise, what would happen is you would assume that the only way to solve everything is gradient descent. There is no better thing in the world, but it's important to know all kinds of techniques. You can also come up with your own ways, your own new ways, and you can also suggest few more ways that we could also do this. And I mean, you could also come up with optimizations. And as you know that even with the gradient descent, you will notice that every year there have been improvements, right? Those improvements happen when people understand what is going on underneath. And there have been at least like 6 to 7 improvements over last 5 6 years. Okay, and this is a subject whereby the even though these equation solving looks like really old technique, but but the techniques that we are going to learn or we are learning are basically under constant improvements. A lot of contribution is coming from across the world. All right, you will be amazed at the techniques that we are learning right now. They're basically some of them have been very recent. Okay, like for example, XGBoost was done in 2014 that we'll be discussing soon. All right, so question from Bo is, so you come up with the equation of derivatives using partial derivative, and then you use linear algebra optimization to find the combination of variable coefficient efficiently. Okay. All right. Let me rephrase. So you come up with the equation of derivatives using, yes. So we come up with these kind of equations by using the partial derivatives. Yeah. So we took this big equation of error. This is error. So this error is in terms of the slope and the intercept of the line, beta 1 and beta 2. And what we're doing here is we are differentiating it once with this, then with this, equating it to 0, right? Why? Because if you think about it, the in calculus, why it is important to equate to 0? Because that's the point where the line will be horizontal, right? Now we get this kind of equation, and then we solve it. Yes. And yes, maximum and minima, that's right. And then use linear uh, algebra optimization to find the combination. Yes. So basically here, this is where, if you think about it, if you have like 100 of beta 1, beta 2, beta 3, right? There will be 100 such equations, right? And you will have to solve 100 consecutive equations in order to get those 100 beta 1, beta 2, or, or theta 0, theta 1, theta 2, right? And therefore, solving this becomes really hard, and you need the linear algebra optimization, specifically the matrix inverse. So finding the solution to finding solutions to the linear combination of such equations is called is basically also analogous to computing the matrix inverse. And the way we compute the matrix inverse is the way we actually do the variable in elimination. If you take a look at the matrix inverse algorithm, it's very similar to the way we eliminate variables. Okay. Question is, do you have to assume that variables are independent? Yes, that's right. We assume that beta 1 and beta 2 are sort of independent. Correct. Basically, they are orthogonal. That's what we assume, that these are something that they are sort of independent, or you can say that even if we compute beta 1 independently, then also we will get good outcome, right? If these variables are not independent, that essentially means that they are not fitting into linear straight line, right? So we'll have to come up with different model in that case. Wonderful. So we learned about the this technique. The only challenge with this technique was finding this matrix inverse. Okay, finding some matrix inverse is basically solving those many equations and so on. Now that became that became a big hurdle, right? So whatever approach I showed you, that gets summarized into this expression. Okay, instead of going all that way, even if you have a million variables, you can just put them in a matrix form, transpose it, do a dot product with itself before transposing, and then you do the inverse, and then you do the dot product with the transpose again, and then you multiply the labels, right? The value of labels, and that's how you get the theta, the cost function. So you don't have to do iterations here. The iterations are only done inside this when we are trying to compute the matrix inverse. Okay, for computing matrix inverse, the technique is exactly like the way we do eliminations, just that that one is a little bit more optimized. There is I forgot the name of that algorithm that people use to calculate the matrix inverse. Okay, but you can just keep in mind that this is very similar to what we generally do to do the variable elimination, right? We remove, we cancel like beta 2, then we computed beta 1, then using beta 1 we computed beta 2, and so on, right? Also, those who are interested in programming, try solving by yourself, try solving consecutive equations. Okay, so why I say this, that like this one, right? let's say, think of it that you're given the array of arrays of 8, 20, 56, 20, 60, 154. Let's say you're given array of arrays, as in you are given two-dimensional array that may be in Python, and you have to find out those variables like beta1, beta2, beta3, and so on, right? So you'll be given this kind of matrix or array of arrays, and using Python, you have to find out beta1 and beta2. Try using the variable elimination the way exactly you will do in order to eliminate, and write that code for yourself. Okay, why I say this, that in one of the interviews long back, I had appeared even before joining Amazon. They actually asked me this, that what we want to know is that can you do this? Okay, being from this kind of background, I was able to do it, but it was important for me to realize that there are many mistakes that we could do while doing the while solving the consecutive equations using, say, Python, and I would recommend that you should try doing it. Okay, now coming back to it, so that's what is the inverse. And that we did last time is that instead of we actually computed using the normal equation. This is the that normal equation way of solving it, and or we could just say linear regression dot fit, and it'll give you the coefficients. Okay, so this is your way. I mean, this is a linear regression way of solving it. Now moving ahead. All right. And I think this is same as what we did just now. Okay, linear regression dot fit. I think it uses the normal equation under the hood. Okay, all right. So that was normal equation. Normal equation is used if your number of columns are less and your data is linear. All right. Now that afterwards we talked about gradient descent. Gradient descent is um, when we cannot just take the error and put it to 0 and calculate everything back. That point of time, you basically combine a kind of iterative approach with the linear algebra approach, and that's what is gradient descent. So you combine that iterative approach as well with the gradient descent. So what you do is you take the error, right? You compute the rate of change of error. If the rate of change of error is too high with respect to a particular variable, particular theta, if the rate of change of error with respect to particular theta is too high, we basically, um, well, I mean, what it means by rate of change of error with respect to particular theta being high, what it means is that if you increase theta, the error will increase. Therefore, it makes sense to decrease theta in order to reach to a point where the rate of change of error is almost zero with respect to a particular theta, right? So and since you have many theta, so what you do is you consecutively solve. You consecutively find theta naught, theta 1, theta 2 all together, right? So you keep on moving these variables like theta 0, theta 1 in order to reach the rate of change of error to be 0, right? Meaning you are on a if you are on the slope like this, at every point you're computing the slope, right? At every point of time you're computing the slope, and you are going in the direction where the slope is going down. If the slope is high, you go really fast. If the slope is low, you go slow, right? And how big a step you're going to take every time is something called a learning curve, right? So so you multiply your rate of change of error with respect to the theta, and you subtract it from that particular theta. That's what is the gradient descent. We also learned about, right? I'll just talk about, we were here in the batch gradient descent. In batch gradient descent, I'll just talk here. All right. So, all right. Our question is, what's the difference between prior linear regression method and gradient descent? Don't we come up with minima using partial derivative and linear? Good question. Good question. So in case of the previous approach, we basically take the compute the compute. We do the kind of linear algebra way, whereby in the previous approach, what we did was we basically computed the rate of change of error with respect to particular theta, and then equated to 0. Correct? Why? Because we knew that we can back calculate thetas from that, right? But sometimes it's not possible to use it because these equations may not be solvable, as well as columns are too high and so on. That's generally, if you're lucky, you got these multiple equations that you can happily solve, or you can compute the matrix inverse, right? So, but that's not true in that cannot be used for every possible problem, right? Instead, we could do a iterative approach. Iterative approach, we go to a point, we initially just take a random point, right? From that random point, we compute, are we, by changing the input, is there any changing in the output? Or by changing theta a little bit, is the error changing or not? If it is, then is it decreasing or increasing? If it is decreasing, if the error is decreasing, that means keep increasing theta. If error is increasing with theta, then keep decreasing theta, otherwise keep increasing, right? So purpose is that by the way of iterative approach, we will try to find out the point at which the of error is rate of change of error is with respect to each thetas is almost 0. So it's a approximation, it's a iterative approach. It's not as direct as normal equation was, that we just took error and differentiated and equated to 0 happily, okay? Because we knew that we'll be able to solve those equations, right? But here, we learned that in case of normal equation, we cannot really solve multiple kind of equations most of the time, and therefore going iterative is a good solution. One iterative could have been that we just sweep the entire area, but that'll require billions of iterations, and still you will not be able to reach. And therefore, uh, greedy approach is what we take. At every point of time, we try to find out where the slope is going, and we just go there. The only challenge with gradient descent in that case is that you might get stuck in the local minima, or you might get stuck at a flat surface, right? Okay, so question is, when is it not possible to use the former method and you have to use gradient descent? Good question. You cannot use the former method when number of columns is too high, right? Because as number of columns grow, the thetas grow, and the more thetas you have, there will be more consecutive equations to solve, and therefore it'll be difficult, right? Imagine what is too many. Good question. Good question. So, all right, let me give you an example. So the complexity of the previous operation is O(n) cube. Okay, what it means? It's very important to know this part. It's a very good question that the computation is done by the computer. So why should it be hard, right? The normal equation, right? The normal equation's complexity is how much? O(n) cube, right? Approximately O(n) 2.6, right? You remember our discussion on the O(n), right? Meaning if let's say there were, right? If let's say there were 10 variables, 10 columns, and that takes around 5 seconds, right? And this one, let's say 10 changes to 20 variables, 20 columns. How much time will it take? Anyone? Right? So it'll take 5,000 seconds. Thank you, Deepak. Okay. Now think about this. If 10 had changed to say 1,000, right? In our classification case, you remember the MNIST? Okay. That'll be 5 into 10 to the power 9 seconds. Okay. No. I made a mistake. So how much it has become? 1,000 times, which is 100 times. So it'll become 5 into 10 to the power 6 seconds, right? So you suddenly see that as the number of features are growing, the time is actually exploding, right? In case of MNIST, you remember we had around 784 columns, that too in an image of 28 by 28 pixels, right? Now, if you think about more such problems, right? Okay, a question is how it is the power of 10 to the, okay, so we are saying that, right? So 10 is taking, say, 5 seconds, right? And let's say that, right? So there's some kind of constant. So when we, you can say that k into 10 cube is some kind of, is equals to 5, right? And the k remains same, and this is 1,000, right? 1,000 cube. So how much that will be, right? Let's say this is a, and you divide these two, k gets cancelled, and the a will be 10 to the power 9 divided by 10 cube into 5, right? Correct? Okay. The important part is that basically this ON cube is done because we don't want to think in terms of constant plus some extra time and so on. We just measure the magnitude. Okay, because it is for developing a hunch, developing the back of the envelope calculation, and this essentially is the art. I mean, not really art, but actually a science, and it's very important for all of you to, when you see a business problem, whether small or big, do a back of the envelope calculation that how much memory it is going to take. Okay. And when you look at somebody's code or somebody's work, look at how many for loops are they using and what kind of complexity it is. And then you'll get a fair amount of idea that, okay, this is going to take huge time and this is going to take less time. All right. So develop that hunch. It's very important to develop that hunch. And the reason why I'm talking about this is because machine learning is not alone mathematics. Okay, machine learning, as you can see, the gradient descent is a great example of the two things overlapping together: maths approach and iterative approach, right? If you are pure computing person, you'll just write an infinite loop and try to swap through the entire area, find the straight line, right? That's pure computing approach, right? Second, and that's like really straight away computing approach. And the normal equation that we used was pure mathematical approach, right? Now, the machine learning is kind of a marriage of the maths and the computing together, and that's where the gradient descent becomes so important. That it is semi-iterative, it is half iterative, half mathematical. All right. So that's how it goes. Great. So we'll discuss some of the very important aspects, and I'm sure that with this, if all of you are with me, and so far, then the rest of the things are going to be extremely simple for you. All right, great. Now, don't get scared with this equation. It's actually pretty simple. All we have done is here, we have taken the differentiation of our theta t. Okay, do you want me to derive it? Or is everybody comfortable with this? All right, let me explain in case you are getting too scared of it. So this is theta, remember? So this is our model, right? Let's say initially we assume some value of thetas, right? And we are given x and we are given y, right? That's our training data. So we multiply thetas, the assumed values, with x, and then we subtract and square it. That becomes our mean square error, right? And when you differentiate mean square error with respect to theta, and so that square 2 comes down, right? And this since we are differentiating with respect to theta, so what is being multiplied with theta? Xi, right? That is taken out here. That is taken out here. Okay, and also note that here the xj, or this is essentially a singular. Okay, so this is being applied over all the instances. Okay, we are saying that overall mean square error is overall rate of change of mean square error with respect to particular theta is this. Okay, so you can think of it this way, that for each of the x, what we do is we basically compute this error and square it, and when we differentiate it, the 2 comes out and the x goes out because that's what is being multiplied with theta, and then we sum it up. Okay, and here whatever is the theta that we are differentiating it, only those x goes out, right? Rest will be 0. All right, so this is how we compute the mean square error. We will show you how to do this, right? So what we are doing here is, once we have computed the mean square error with respect to each of the thetas, what we do is we basically combine them together, create a single vector, so that we don't have to carry around individually in a loop. Instead, we'll carry around in a vector. Now, here, this is the general way of computing mean square error. Rate of change of mean square error with respect to each of thetas is 2 by m. Whatever is our input training data, the transpose of that, dot x dot theta minus y. All right, that's how it is. It's actually pretty straightforward to derive, and yeah. So this essentially this way of, once we have computed the error, what we'll do is we'll basically, for each of the thetas, what we'll do is theta in the next step equals theta, which was in the previous step, minus some constant. This is some constant. We call that this constant as learning rate. Generally, we take its value as 0.001 or 0.01. And this constant becomes very important, because if you take this as really high, what will happen is on every step, the thetas will jump to the other side and will keep going away and away, right? So this constant learning rate is actually the hyperparameter tuning that we did in the end-to-end project. That's this one. This is one of them. We generally try with 0.001, then we'll try 0.001 and so on, right? So the overall algorithm, because this is something that we can't really figure out using gradient descent. All right. So this is a quick implementation of the same thing that we keep on, let's say we take some amount of iteration. Uh, Again, here every time theta will go down, right, or go up based on how the error is going. There's no definite way of saying that we are done. Okay. Okay. A question from Deepak is, what is delta theta? You mean to say this, right? It's essentially rate of change of mean square error with respect to theta. This is the derivative that we calculated here, right? So in a single shot, we are computing all the thetas using this, okay? Using this. And just an example here. Again, gradient descent is a semi-iterative approach, and the iteration goes towards local minima, meaning let's go to the direction which is giving us great results. It's as good as that. All right. And there is nothing wrong in this approach, just that sometimes we get stuck in the local minima or on the flat surface, right? Sometimes when we are too greedy, then we end up having less outcome as compared to the greater outcome. And that's the downside of gradient descent, right? That we, I mean, let's say there are multiple minimas in an equation and there could be better ones. Therefore, the batch gradient descent will just give you the local one. It becomes a function of initial values of theta, right? And how do we decide initial value of theta? It's just a random initialization, right? So we start with, let's say here we're saying eta equals 0.1, number of iterations is 1000, number of instances is 100, and we are initializing thetas with some random numbers. And here what we're saying that at every point of time we are computing the gradient. Since it's a linear equation, the gradient is pretty simple to calculate. But good news is that we can actually compute the gradient even if we do not know the state equation, right? Using the first principle by just changing the value a tiny bit and then observing. So using the standard computing way of calculating gradients, we could do that, right? As I described you earlier. So here, in case of this, the gradient is basically from a mathematical formula. And even if this is not available to us, we can compute gradients using some other technique. As we'll see in case of neural networks, we do not know which equation to use to compute the gradients. Therefore, there we will be using the numeric way of computing the gradients. Okay. Then once we are done with computing the gradients, then what we do is whatever were the theta initially, right? We subtract from that theta, this eta multiplied by gradients, right? Eta is a 0.1, 0.01, or 0.001 or something. Now here the important part is the gradients. Here we are basically calculating all the thetas in a single shot. Okay, we are calculating thetas in all of the thetas in a single shot. This is essentially an array of values. This is essentially an array of values. And this is again an array of values, right? Or you can say a vector, right? And this, yes, theta is a vector. Theta is a vector, gradients is a vector. while eta here is a number. All right. So a question from Deepak is how the previous equation, this equation, okay, this one, all right, all right. So this is essentially, I'll explain it, right? So let me see. So we want to figure out how this came, right? So y predicted is what? Y predicted is, let's say, let me put it this way. So there is x, right? Or you can say capital X and y, right? And right, and the way we look at it is there are some thetas, and if you do a dot product of those thetas with xt, right, you will get y, correct? Or can I explain it in a better way? So imagine this, that we are saying, let's say some values of theta 0 and theta 1, right? We are doing a dot product with 1 here and x here, right? And we are saying some values like y1, y2, correct? Meaning what we are saying, theta naught plus theta 1 multiplied by x1 equals y1, okay? Yeah, so I think this is for one variable, and had it been, okay, so all right, so or you can just say that here this, correct? So theta naught, I mean, if given a data, what we say is that let's say we are given this, let's say this is your x and this is your y, right? It is some values and some values, and similarly this is some values. So we essentially want to come up with some kind of function, such that when we multiply that with the function, yeah, this is not this way, it is basically x into something like this equals y, right? This way. So we want to come up with the set of thetas such that we we are able to predict y, right? So these are our numeric values, right? So what we could do is for this set we could come up with some values of thetas, and such that when we do dot product of these two, we will get y, right? That's about it. Okay, so let me, how best I can describe this. Let me just see if we had a good slide on this. All right, is this clear to you, this one? All right, so when we differentiate this with respect to thetas, then we will basically get that equation, right? The 2 will come down, right? 2 will come down and xj will go out, okay? right? So here, yeah. So when you differentiate, it's basically the same thing, the same equation whereby we are differentiating that with respect to theta. All right. And once we have computed, okay, so this one is clear to you, right? That for particular theta j, what we do is we overall computed MSE, the overall MSE, okay? Overall MSE, we differentiate that with theta j, correct? A particular theta. And once we have computed this, we do that for all of the thetas, right? Theta 0, theta 1, theta 2, and so on. And when we do that, what happens is this gets gets translated to this, okay? Because if you think right, if you think about it, this values, this essentially um, the small x, which is each row is getting converted into capital of this one, right? So so basically when you put this one x, capital small x becomes capital X when you put sigma around it, right? The last x is basically, you can think of it, it came before, okay? So you can actually, how can I um, derive to this? Okay. So when you put all of them together, right, what we are trying to do is we are trying to compute the sum of each of these values, right? And sum of each of these values. And if you put them together like 0, earth, 1, 2, and so on, then then we will get this. So the last one will become something of this sort and so on. Can I, maybe I can derive it somewhere. So this last one, this you see comes ahead, okay, and so on. Just that, I mean, this is just intuition, but there's a linear algebra way of deriving it till that point of time, okay. So what's happening here is we are saying the summation of all of these values is mean square error, and for each of these variables we could put them in a big array, and when you do that, the overall MSE is comes out to be this, okay. All right. All right, because the dot product, if you think about it, it's going to sum up everything anyway. Therefore, the sigma has gone, and the small x is converted into capital X. All right. So, I mean, it's basically an intuition you can develop. I can have a separate derivative. I mean, I can derive it separately. Okay, and essentially it is this. Okay. And you can try it with just two variables like theta 1 and theta 2 and x1 and x2, and you'll get a clear picture. Okay, so try it with just two variables using this way, and you'll get a clear picture, right? So this is basically the error. And also honestly speaking, that in many scenarios you will not really be worried about calculating MSE this way, because rate of change of something can be computed using the definite way of doing it. Remember the first principle in derivative, like f of x plus delta minus f of x divided by delta x, right? we'll be using that way in most of the deep learning. Now, question from Deepak is that last X is also vector. This one is a matrix, right? This one is a matrix. This one is a matrix. And last one, uh, this one, right? This one, xj. Yes, it's a vector. Just is it a vector? So we are saying that differentiate it with respect to theta j, and no, I don't think it's a vector. Okay, it's not a vector. It's a singular value. All right, because okay, so we are here at this point whereby we computed the MSE overall by combining all the gradients and by coming up with this kind of thing. Is everybody okay so far? Okay, since it's linear regression, we are assuming that the relationship between our thetas to the outcome is linear, right? Therefore, such kind of equation can be derived, right? Had it been really complex equation, we would not know. Okay, we would not be able to calculate the MSE this way. Now, once we have done that, what we're going to do is for each of the thetas, we are going to compute, for each of the thetas or for all of the thetas, we're going to compute the next value by subtracting a multiple of the the derivative of that, right? Basically, theta 1 in the next step will be theta 1 minus eta into rate of change of total overall mean square error with respect to theta 1, right? Similarly, theta 2 will be like that, theta 3 will be like that. And as we discussed, that writing a for loop is generally clumsy. Instead, we can get the same thing done using NumPy and using the linear algebra way, right? So essentially, to avoid that for loop, because the same thing can be very well achieved by using vectors, we're going to have the singular equation. All right. So here you can see that the theta is a random number having a dimension as 2 by 1, right? Meaning 2 rows and 1 column. And we are saying that at every point of time, we are computing the overall gradients using this kind of formula, and that's it. This is our theta. Now, this is learning rate, right? Learning rate is a constant or hyperparameter. This is the number of iterations. Notice that here there is a number of iterations. Lots of discussions revolve around how many iterations should we have in case of gradient descent, right? We'll talk about it very soon. Now, number of elements in a training data set is M, okay? That could be really huge or really low, right? The thetas are a function of how many features do you have, how many columns do you have, right? So you multiply each column with a theta, and that gives you the outcome, which is y, right? So what we're doing is we compute the gradients here, then we subtract, okay? And that's all. So, and after let's say 1,000 iteration, we are getting very similar results as the normal equation, right? As the normal equation. Generally, the normal equation gives you similar result as gradient descent. Okay. Now, the learning rate, the eta, we call that eta. We draw it like n with this. We draw it like this. We draw it like this, right? And a question is from Deepak, where in this iteration we are getting the minimum? I mean, that derivative 0, right? So good question, good question. So here, this is where we are calculating the derivative. We are not computing the derivative. We are just using a formula like this one, okay? Basically, whatever we just showed you, it is this iteration. In every iteration, we are going to compute this, okay? So you can think of it like theta equals theta minus this. Every time we are updating thetas, and we are doing it 1,000 times. Good question. Question is that how do we know that it is minimum finally? We do not know this way, right? We are just going with the iterations and we believing that this will give us great results. Okay. Question is that how do we know that these many iterations are sufficient? Okay. So again, number of iterations, or we call it sometimes number of epochs, okay, is basically a hyperparameter, and it's a hidden trial. Okay. Okay. And there are multiple mechanisms to determine how, when to stop. Okay. Main challenge with gradient descent is when to stop or when not to stop. There are multiple ways. One, we stop when things are not going down. Second, we just run it a fixed number of times. Okay, and so on. So we're going to go into that detail more. Okay. So essentially, right now we do not know how many iterations we are going to go, and there are multiple ways of determining when to stop. Okay. Now, these are hyperparameters. Number of epochs is considered hyperparameter, meaning iterations are, this is hyperparameter, this is hyperparameter. Okay, meaning when we initialize most of the algorithms, we'll also give number of iterations as argument. Now, moving ahead, how the learning rate affects the gradient descent. Let's just take a look. This is the learning rate, eta. What is eta? Every time we are multiplying eta with the gradients. Okay, it could be something, right? Now, if we plot this line, right? This is our data. This is our data. Initial line that you see would be somewhere here. Then it'll keep on going up, right? Why is this going up? M and C, both the slope and intercept, theta 0 and theta 1, both are changing such that we can go near this, right? We can go near this. So it's continuously changing such that in the first iteration it was here, second it was here, third it was here, right? If the eta, the learning rate is too slow, what will happen is the impact of gradients on the change is going to be very low. Therefore, even after some iterations, like 10 iterations, we are far away from the actual value, correct? If the eta is high, which means we are going to multiply the gradients with a bigger number, therefore, the impact of gradients is going to be high, right? And if the eta is too big, right? If the eta is too big, what's going to happen is it's going to be disastrous. You see, initially, the first line was here somewhere. At this point of time, it computed the error. And then based on the change in error at this point of time, it changed the slope and the intercept. And because of which, since this is eta is used, therefore the change in Theta's is going to be really huge, and therefore it just jumps to the other side. It just jumps to the other side, probably here, right? And then again computed the gradient. Since now the distances become far more, the gradients are even further. And when we multiply this, instead of coming here, we'll jump back down. And then that will keep on going, it'll keep on diverging instead of converging. So eta is a little, so in general, when you plot your, how is your error converging? If the error is not converging, it's diverging, that means your learning rate is too big, correct? Your learning rate, the eta, is too big. All right. Now, if the learning rate is too low, it will basically, even after 10 iterations, it will not go anywhere. Algorithm will take a lot of time to reach there. Okay. A question from Bo is, what do you mean by error is converging or diverging, right? Meaning, if you see, uh, at every step, okay, here, this was the first line drawn, correct? Then this was the second line, this was the third line, this was the fourth line. So we are kind of approaching the the one, that line that is going to fit here, correct? So, and how is that happening? At every point of time when we drew this line, it is going to compute the rate of change of this error with respect to the slope and the constant. And if that error is, the rate is too high, right, then it'll basically change slope as well as constant accordingly, correct? That's what it is going to happen. Now in the second case, the, let's say first line was somewhere here, second line quickly comes here, third line comes here, and the rate of change is also decreasing at this point, correct? And therefore it'll settle down somewhere here. Right? But here the crazy part is that we started, let's say here. Now we computed some gradient, and that gradient came out to be too big, right? Because since it's far away, therefore rate of change will be too high with respect to M and C, right? Or even if it's not far away, the rate of change is, let's say, too high. What will happen is, if our eta is too high, we will, let's say, multiply slope by too big a number, so we'll reach here, right? And since it's now on the other side, let's say, now the gradient at this point, when new line is here, new thetas are here, the gradients are going to be again computed, and this time the gradients are negative, so we'll decrease the slope as well as intercept, and suddenly we will again go somewhere here. Then we will again check whether how are the gradients. This time we'll even say that the gradients are further higher, gradients are really high, and in that case you just keep on jumping to this one. So further and further, and we will end up with diverging instead of converging. Instead of coming to this, we're going away from this. All right. Okay, so this is learning rate too low, and algorithm will take a lot of time to reach the solution, right? And if the algorithm, if the learning rate is very good, meaning one of the hyperparameters called learning rate is very good, in few iteration we would get a good solution, right? But if the learning rate is too high, the algorithm diverges. It's jumping all over the place, and it's getting further and further away from the actual solution, right? Now, question is, how do you find good learning rate, and how do you find good number of iterations? Those are the things we are going to discuss. Now, to find a good learning rate, we remember our grid search from end-to-end project. Towards the end, we had a section called hyperparameter tuning. There we talked about grid search. Yes? Everybody remembers the grid search from end-to-end project? Okay. So generally what we do is using grid search, we find the learning rate. Okay. Now you can see that in machine learning, we use both the approaches, iterative as well as mathematical, correct? And the overall idea is to come up with, given a lot of data of the history, to come up with a certain correlation, which would give us great predictions, right? So here, using the grid search from the end-to-end project, and we can find the good learning rate. Now, okay. Sometimes the random search also helps, or we can limit the number of iterations so that grid search can eliminate models that take too long to converge. Okay, grid search can eliminate models that take too long to converge. Second question that Deepak and Bo asked earlier, that how do we know that? How do we know that which are the good number of iterations? Okay. Again, if the number of iterations are too low, then we may not get optimal solution when the algorithm stops. If the number of iterations are too high, then our time may be wasted and algorithm may not converge, right? So, so how do we find the number of iterations? Okay, one of the ways is that we set a very large number of iterations. Okay, and the moment the error is not going down, right? If the rate of change of error is not below certain tolerance, we keep on doing it. In case we reach to a point where the overall error has dropped below a certain tolerance, we we basically stop the iterations. Okay, so this is another way that at every point of time we will basically let it keep on going, and the moment the error has gone down below certain value, we break the loop. Okay, we stop at the point. All right, so the convergence rate for mean square error, right? The convergence rate, how fast it's going to cover, is inversely proportional to the number of iterations. If you have more number of iterations, the convergence will be, I mean, the error will be low. If you have too many iterations, the error is going to be low. If you have too few iterations, the error is going to be high, right? So, okay, quick question. In a particular model, if we have few iterations, will the model be overfitting or underfitting? Very less number of iterations. That's right, underfitting. Perfect, perfect. I'm extremely happy, okay, to know that, and that you got the idea. So when the iterations are low, that means our model is going to be underfitting. Why? Because it has not really learned and it has not really reached to an optimization. It'll perform bad on training data as well as on the testing data. Okay, so if we divide the tolerance epsilon by 10, as in the precision or the mean square error, if we want 10 times lower, we will have to increase the iterations 10 times. Okay, that's the idea. So in very simple words, the more number of iterations you have, ideally you should get the lesser error. Okay, lesser error. This is batch gradient descent. Batch gradient descent is the first algorithm whereby you do we are doing the calculation of mean square error over all of the data points, right? And then we are computing the rate of change of individual theta based on the overall mean square error, right? Good. Question from Deepak is, how do we decide number of iterations? Okay, by tolerance, that's right. So what we do is we set our iterations to be very, very high, and we break the moment the mean square error has dropped below certain point. Okay. All right. Again, this is again a little bit of a hidden trial that you will start with 100 number of iterations, and you see that, okay, even at the end of 100 iterations, it is going on. So we'll try with, say, 2000 and so on. Let it keep on going. Okay. Question from Deepak is, what normally is the tolerance value? Tolerance value could vary from project to project. Okay. And there's no straight away answer. The general thumb rule is that let it train, and we run the iterations. We observe that what point it stopped going below certain value, right? Because what will happen is initially in the beginning, the steps are too big. Okay, so where is the, yeah, you see, in the beginning, first iteration will basically quickly jump from, let's say, here, imagine that it was here, it'll jump very high, where there'll be huge change. Then the change will be too high, again, little lesser, then lesser, then lesser, then lesser, and then lesser. And this way, as we approach the optimum, the change of between the previous iteration and next iteration keeps on going down, right? And ideally, at this point of time, ideally, if all these data points are exactly in the same straight line, the rate of change should become zero, but it does not become zero. Okay, it does not become zero, or mean square error does not become zero. Therefore, we need to keep certain threshold, and you do not know threshold in case of each project. So what you do is you just run the model or train the model for some time, and then keep observing that from which point the errors have started becoming insignificant, and use that as a epsilon, or you can say the the error that you are okay with. All right. No, not clear still. So start with large iterations, and you interrupt it in case the error is not going down beyond a certain value. Okay. All right. Okay. All right. All right. Wonderful. Now the second way is stochastic gradient descent. The batch gradient descent that we just did is slow when the training set is large, right? Because what's happening in case of the normal gradient descent is that we are using the whole training set to compute gradient at every step. Question from Sumit is, do we use linear regression in real time? We do actually. Okay, that's the first algorithm that we try, and we use it. Yes, you'll find that many projects are actually can be done very well with gradient descent. But today,
These techniques have moved to deep learning, and you'll notice that the deep learning is essentially about gradient descent. All right, the same technique becomes more and more complex by using multi-layer of neurons. Okay, so yes, so whatever we are learning, the linear regression is used in many projects. Okay, though we compare all the approaches, whichever is giving us great result, we stop there. Okay, and we just compare. We do not believe in the hunch that maybe the linear regression will give better results, or SVM, or decision trees, or deep neural network. We'll let the grid search figure out. Wonderful. So the problem with batch gradient descent was that it was slow when the training set is large, because it was using the whole training set to compute the gradient at every step. You're using the whole training set, all the axes, all the rows or record, or you can say instances. Using all those instances, we were computing the mean square error, and using that we were computing the gradient, right? So it's generally very slow when you have number of records to be too high and you want to train it in real time. You can't really use batch gradient descent because it's going to be slow. Also, it requires more memory to be loaded in the it, it, you need more bigger RAM because it loads the entire data into the memory. Now, on the other hand, the stochastic gradient descent just picks a random instance in the training set at every step and computes the gradients based on that single instance. Now, this is another extreme, that instead of computing the overall mean square error on all the instances, right, for a particular set of thetas, instead of computing on all the instances, it'll just compute the error using one single instance that we have picked up randomly. Okay. And it computes big gradients based on that single instance. Now, this makes the algorithm really, really faster, as it requires very little data to be manipulated, right? So huge training sets can be trained even if the data is in petabytes or gigabytes. It doesn't matter for gradient descent, because you could just pick an instance randomly from the dataset, compute the gradients, and change the thetas in accordance with the gradient descent, right? So now, if this color, if we plot, there are two thetas, theta 1 and theta 2. These are the, let's say, two model parameters that we are trying to optimize. Let's say we are trying to figure out theta 0 and theta 1 such that the error is minimum, meaning we want to reach here. Initially, let's say theta 0, theta 1 and theta 2 is high. So maybe or low, let's say here. We were here at theta 0, theta 1 and theta 2. Let's say here. So here, what we have computed, we have taken some value of theta, some value of theta 1 and theta 2. At this point, you can see that the error is too high, or cost function is too high. Black means high, okay? White means low. So if we keep on just changing thetas, okay, we will cross this line like this. Just let's say we are just changing theta 1, not changing theta 2, correct? And if you're just changing theta 2 and not theta 1, from here, we'll just keep on going in the straight line, correct? Now, that may not give us great result, right? So you'll have to vary theta 1 and theta 2 both at every step, correct? Based on their gradients, right? Right? Uh, and this way basically, what we are trying here is that at every point of time, imagine that initially theta 1 and theta 2 that we randomly selected were here. Now, we compute the gradients at this point, meaning the slope at this point, and quickly changed both theta 1 and theta 2. We'll go here, 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 keep on repeating it, and we will reach the center. So you can see that here in case of gradient descent, in case of stochastic gradient descent, it is just roaming around just too much. Instead of straight away going to the center, it's just roaming around too much. And that's why there's basically this stochastic gradient descent problem, that it basically roams around just too much. Okay, why? Because every time what we do is we just pick one instance, compute the gradients, and then update the thetas. All right, couple of questions. First question is from Bo. Is there some kind of ways used to make a stochastic method to be more effective? Yes, yes. Somewhere between stochastic and batch, there is mini batch. Okay. A question from Sumit is, just wanted to know if there is a way to test each method to get accurate result with the use of simple data set, sample data set? Good question. Good question. So yes, this is where the cross validation that we discussed comes into play. Okay. All right. So you should give it a try. There are all the methods like batch gradient descent, stochastic gradient descent, and mini batch. All of that is available. You could give it a try. Okay. So stochastic gradient descent, since it's basically picking up one instance, and based on that, it's just changing the slope and changing the thetas, or changing the thetas. Because in our case, in case of linear regression, we're trying to figure out a line which has got some slope and some kind of distance from the center. And for that, we used multiple techniques. And one of the techniques that is there is gradient descent, and one variant of gradient descent is stochastic gradient descent, whereby we just pick a random instance. Now this is stochastic gradient descent is good in many terms, but it's also equally bad. The cost function bounces up and down, decreasing only on average, and over time it ends up being very close to the minimum. But once it's get there, it continues to bounce around, never settling down. So you can see, even if it came into this zone, the white zone of error, which is like really low, right? So still it is jumping around. Instead of just silently coming nicely from here, following the radius to the center, it is basically jumping around a lot. Okay. A question from Sumit is, I have missed some classes, we'll cover and discuss on the forum. No, you can ask it, ask these questions. It's completely okay. All right. So yes, the method, the cross-validation method, I think everybody is okay. So in cross-validation method, what we do is we basically take a list of approaches and try it, okay, and see which one is giving us great results. All right. So once the algorithm stops, the final parameter values are good, but not optimal, as algorithm never settles down, right? It never settles down. So when the cost function is very irregular like this is a very irregular function. It has multiple minimas and multiple maximas. In this case, if you think about it, when you differentiate such kind of cost function with respect to any theta, you'll have like multiple solutions to it. One, two, three, four probably. There'll be four different solutions to this, and that means that it's going to be really hard to use normal equation for such kind of thing, right? So in such cases, when your cost function is a little too complex because your for whatever reason, whatever equation that we're using is not non-linear and so on, in those cases, the batch gradient descent was just jumping to the local minima, right? Let's say here, it just quickly jumps here, stops here. Similarly, if it's coming from this side, the moment it hits the plateau, it'll basically settle down there. right? That's basically the, was the downside of batch gradient descent, right? When the cost function is very regular, then SGD, the stochastic gradient descent, is generally better at finding the global minima than batch gradient descent, as randomness may help algorithm to jump out of the local minimas and find global minima. Okay, so stochastic gradient descent, since it jumps around a lot, the chances are that it could get better results than the batch gradient descent.
All right. So we learned about the batch gradient descent. In batch gradient descent, all we do is we compute the overall mean square error or rate mean square error, and then based on that we change or tweak the thetas, and that's what we do as part of batch gradient descent. Now, or you can say that for some thetas, what we do is for each of the value of theta, what we do is we just check the error over all of the instances, and we tweak our theta based on that. Now that's little too much, because if you have a million instances, you're going to find out the MSE for all of the instances. That's going to take huge time, and that this is happening on every epoch or every iteration, and hence the batch gradient descent could be really slow. So the other extreme is the stochastic gradient descent, in which case on every step we just pick one instance and find out the gradients with respect to that one instance. And this way, instances in rows records. Okay, and we find out the MSE, mean square error, with respect to that particular instance which we have picked randomly, and we keep on doing that over and over again. Based on that, we tweak our thetas and so on. Because of which, stochastic gradient descent is actually um, better to get out of the local minimas, because it doesn't every time it's jumping around and moving ahead. And the only problem is it just dances too much. It just roams around too much, and that's why it is not a great solution, right? Therefore, what is the solution? In case of stochastic gradient descent, there is an idea called simulated annealing. So idea is that we gradually reduce the learning rate, meaning we curtail or control the learning rate, meaning as the time is going, we keep on decreasing learning rate so that it does not jump around too much. The steps start out large, meaning in the beginning the stochastic gradient descent moves little too much. Okay, this helps us make a quick progress and escape the local minimas, and then steps get smaller and smaller, and this helps the algorithm to settle down at the global minima, right? This process is called simulated annealing because it resembles the process of annealing in metallurgy, where molten metal is slowly cooled down. Okay, so basically, initially the change is too high and then it settles down. Okay, so to create or get the simulated annealing in place, we use something called learning schedule. Essentially, this is a function that determines the learning rate at every iteration. Okay, at every iteration, the gradient descent algorithm will call your function to check what should they keep as learning rate. Okay, if the learning rate is reduced too quickly, we may get stuck in a local minimum or even end up frozen halfway to the minimum. If the learning rate is reduced too slowly, we may jump around the minimum for a long time and end up with a suboptimal solution if we halt training too early. Okay, so we can implement the SGD
Okay, and let's implement it. And by convention, we'll iterate by rounds of m iterations that we have been doing. And each round is called epoch. Though we are using a wrong sign here, but just italic m is basically the number of iterations. Okay, so generally m used to be our number of instances. Here, basically, we iterate m with m rounds. Each round is an epoch because every time we are just picking one uh, instance. Therefore, m here does not mean that. Okay, let's just take a look at the notebook. All right, let's just try to take a look at the notebook, and my ML folder is here. Then we go to machine learning and then training linear models. We're going to implement the stochastic gradient descent, and there we are going to. All right, so let's let it open. I think that'll make more sense. All right, let's just run the cell. Okay, let's keep moving. Okay, let's just run everything. Yeah, last time we talked about this, right? The differential. Everybody's clear about how to calculate differential in real time, right? This is basically the first principle of calculating differential. We are calling this and so on. I think we discussed this in class, right? Okay, so here we go. We move ahead. Yeah. So here I want to show you that when we are plotting the gradient descent like this is how it looks like. Okay. Earlier, it is that batch gradient example whereby learning how it is varying with respect to learning rate. We wanted to show you that. All right. That's basically mentioned in the notebook. Okay. So here we are trying to show a simple implementation of gradient descent, which is stochastic one. And we are just keeping a note of the thetas that we want to, whatever thetas we have encountered, right? So let's take a look at this. So here what we are saying is that we are defining a learning schedule function. What it gives is that as the time goes, time increases, this this keeps on returning a smaller value. So we are saying that 5 divided by t plus some another constant, right? So basically, as t keeps increasing, this value keeps on dropping down, right? And based on learning schedule, we will be calculating. Okay, we will be basically moving ahead. This is based on this. We'll be calculating the eta, the learning curve, learning rate. Now moving ahead. So this is the initial thetas, as in a random initialization of thetas initially, and then this is the path that we are going to just keep a record of where all we went, right? And this is for recording purposes. Now here we are saying that for 50 times, this is for 50 times, for each of the records in range m. Now m is how much? Okay, m is length of xb. Okay, now what we are saying, let's just keep it aside for time being. This is for the presentation purposes. Here we are saying that generate a random number. Okay, generate a random number for every time. And what we do is we basically pick a random value. Okay, we pick a random value here. So we are saying that xi is from that random index to 1 plus value, right? That means we are just picking the x with in that range. We could have used random index just like that, but that could have been disastrous because it will change the dimensions. Okay, xp is a two-dimensional array, and we want a two-dimensional array with the right with one column, one row, and all columns. Correct. Similarly, y we are picking up this range without changing the dimensions. Correct. And then we are computing the gradients. Notice that here we are basically computing the gradients based on xi and yi, not the capital X1, right? So here this is that individual gradient for this particular record and so on. This is our gradient. Now eta is, in this case, it's variable, right? So this is how eta looks like. So what is it? What's happening here? For calculating eta on every step, we are asking learning schedule to do it, right? And here we're passing the number of iterations. How many iterations have been there so far? So total number of epochs in the beginning multiplied by this epoch multiplied by m plus I, right? Those many iterations have happened so far, and we're calling the learning schedule function, and using that, we are calculating the eta, right? And afterwards, we are using eta and the gradients to compute thetas and keeping a record of the thetas that we have so far seen. Okay, we are keeping the record of thetas that we have so far seen. All right. So this way you can see this is an example of stochastic gradient descent, whereby we are also using our learning schedule, right? A question from Deepak is, what is x underscore new underscore b? X underscore new underscore b is basically the data with the bias, one extra number, right? Yeah, it is same as the x underscore b. And x underscore b looks like this. All right, where did we go? We are here somewhere. X underscore b is normal x with extra one. All right, so moving ahead. So here what we're trying to show you is this part, right? So initially the you can see the initially this is where it starts, and then it starts decreasing, and further since we are decreasing the learning rate, it's not jumping anymore, right? So this is what we did in case of stochastic gradient descent. We basically did one more thing in stochastic gradient descent, is that we applied the learning rate. Okay, so you can notice that in first 10 step, uh, the steps are really regular. You can see initially it's here, then finally it is starts settling down. Okay, so to perform linear regression, we can use scikit-learn's out-of-the-box method called SGD regressor class. By default, optimize the squared error cost, right? So all we need to do is import SGD regressor from the sklearn.linear model, and then okay, after importing, we can initialize SGD regressor with number of iterations and penalty and ETA. We'll talk about penalty very soon. Okay, and then once we have initialized, then we can just call fit, and that will generate the intercept and coefficients. Intercept and coefficient are the ones that is called the what do you say, the model. Okay, So number of iterations is a hyperparameter, the ETA is the learning rate, and penalty is something called regularization that we're going to cover very soon. All right. So here what we're doing is, here there is learning schedule, that's okay. And we're saying go to number of epochs, print. If the epoch is divisible by 50, meaning every 50th, it is going to do some kind of plot, right? And so on, right? Afterwards, it's picking up xi, yi, and computing gradients, and ETA is computed based on the gradient learning schedule, and theta is equal to this. Okay, great. So all we need to do is we have to call the SGD regressor, import it, then do a fit, and that's it. Okay. And before this, okay, so there's a word that we've used here called Ravel. Ravel is basically converting any multidimensional array into single dimension array. That's called Ravel, right? So let's say the y1 is like this, okay, or let's say y is something like this, right? A single, like a, multiple rows and single column. But when you do a wider travel, you get a single factor. Okay, so Ravel basically converts that, and here we are doing that. We basically calling SGD regressor on our x and y. That's all. Okay, using that we can do prediction. All right. Question from Alsair is, how do we know which model, which line gives the best model? Okay, good question. So regularization we'll be talking about very soon. Question from Alsair is that how to know which line gives the best model for the prediction? Okay, so basically the last lines where the iterations are increasing, those are the ones they would give you better results than the other ones. Okay, also after a point of time, when you keep on increasing iterations, the as you keep on increasing iterations, you will keep on getting more and more accuracy. But the moment you reach kind of a optimized value, it would not decrease, it would not any further improve the results. Okay, so so the ones that are towards the end where the iterations are finishing, they should generally give you the best model. And the only way to basically get the best model is by comparing multiple models with respect to results. And that's how you come up with the best model, by iterating and comparing. All right. A question from Deepak is how to search some text in this Jupyter notebook. You can say Control F and you can search. Question from Al Sayed is how to have the equations for these equations. I mean, in showing results, we need equation to describe. In showing the results, could you help me understand the question? You mean like when we are plotting this? Is that question that how do we? Okay, once we have, you mean to say that once we have trained it, how would we find out the best line? Is that your question? All right. So first of all, actually this whole exercise is about finding that line, correct? At every point of time, these thetas is what we represents. These thetas are what represents these lines. Okay. So theta 0 means the distance from the center, and theta 1 means something that's multiplied with first feature. Okay, theta 2 means something that's multiplied by second feature. All right. So theta is actually the slope in the line, slope of the line, slope and intercept. If you see even here, not here, yeah, you can see every model gives you these values. Every model gives you these values. Do you see that? Have I understood your question correctly? I'll say it. Deepak's question is how to search some text in Jupyter Notebook. You can use Control F. How to, okay, great. So one thing that we learned was the SGD. SGD basically makes it extremely fast to reach to some point, but SGD also stochastic gradient descent also basically roams around a lot. Okay, it takes long time to converge. Now, as a balance between the batch and stochastic, there is something called mini batch. The last gradient descent algorithm that we'll look into is mini batch gradient descent. It's quite easy to understand as we know both batch and stochastic gradient descent. Is that at each step, instead of computing gradients based on full training set in like the way we did in case of batch gradient descent, will be, or using only one instance, like the way we did in case of stochastic gradient descent, we do we basically use a mini batch to compute the gradients on a small random set. Okay, these are called mini batches. All we do is instead of computing the mean square error and as well as the gradients on the whole data set, we pick the mini batch instead of entire batch. All right, instead of entire batch or a single record, we pick the mini batch. Okay, rest of the mechanism is exactly like batch gradient descent because mini batch is a batch, right? So the main advantage of mini batch over gradient descent, over stochastic gradient descent is that we can get performance boost from hardware optimization for matrix operations, specifically when you're using GPUs. Okay, so mini batch basically gives you the ability to get the best of both worlds. And in case mini batch is taking too much time, even for you, what you can do is you can use the other like other ways of optimizations, just such as matrix multiplication, matrix operations like GPUs, and so on. All right. So basically, this is one of the advantage. Mini batch algorithm is less erratic as compared to SGD. Okay, and SGD basically goes more closer to minimum than, sorry, the mini batch goes more closer to minimum than SGD. Disadvantage is it's harder for mini batch to escape from local minima. Just like batch gradient descent, the mini batch has lower, similar to batch gradient descent, and unlike stochastic gradient descent, the mini batch also kind of gets stuck in the local minimas. Okay, so mini batch gradient descent section. Let's take a look here. So this is how we will implement the gradient descent. So the mini batch gradient descent. The important part out of it is this part. Okay, so all we are doing here is we are running the loop these many times, correct? We are shuffling the indexes. Okay, so what we are not shuffling the indexes, we are generating certain random permutation out of m, out of these values. Okay, all right, so let me say, so random permutation m means give me a random permutations of indexes m. Okay, of indexes m.
Now, once we have done that, using this, we are shuffling our data, right? Using this, we are shuffling our data and both X and Y together. And once we have done that, we could iterate over we could basically compute generate the range. We could go from 0 to M, and in every step we are increasing the value by this size, okay, in a step of this much, okay, and every step we basically increase T, right, and Xi is basically from this window. So what we do is, out of all the instances, we are going to pick a smaller window, and using this window, this small window size, right, this window size, we are picking X and Y, and afterwards we are finding the gradient based on X and Y, and then we are generating creating the learning schedule like eta, right? And just like we did above, and then we are computing the next theta. All right. So the main difference between this and SGD is this portion. Okay. So we are using a mini batch for the computation of gradients instead of entire batch. Question from Deepak is, initially we don't know if we have multiple local minima in the cost function. Then what is the basis we should select SGD, BGD? Should we always use SGD? So general thumb rule is that start with SGD and then we'll do the optimizations. Okay, that's a general thumb rule. All right, so I think these two things are exactly identical. We have just copy pasted these two in order to test it on number of iterations more and so on. I hope everybody is clear that here we are picking up mini batch size and then running it. So all we are doing is we are going these many number of iterations, shuffling the data. This is our shuffle data. Then we are picking up many batches, and then we are picking up many batches, and then we are computing new thetas. All right. So as we can see that for each epoch, we are creating mini batches from the training set, right? So all we did was we created the mini batches, and let's just compare the batch, stochastic, and mini batch gradient descent, and then okay. So now here are three methods. You see that? Here you can see theta 0, theta 1. These are what? These are the parameters, meaning uh, somewhere first theta 0, theta 1 both increase and keep on going, and then they both start decreasing. Now here basically they're moving, and imagine that these are the perfect values of theta 0 and theta 1, right? This is how it looks like. So batch gradient descent, you can see, is the most stable one. You see it here. This is most stable one. While the mini batch is this. Mini batch is relatively better than stochastic gradient descent. You can see stochastic gradient descent starts from here and roams around just too much. Okay, roams around just too much. So this is a good comparison of gradient descent as compared to the various variations of gradient descent, right? Any other observations you have on this, everyone? No observations? So the objective of this graph is, or these three approaches here, is on the basis of the on the basis of how big a batch we select. So we are comparing the
gradient descent, the stochastic versus batch versus mini, right? So a question from Deepak is, are we varying learning rate in mini batch? Yes, I think we are varying, right? So you can see, correct? Any observations? All right, moving ahead. So all the three algorithms end up at the same minimum. That's first observation you see, that all of these ones are ending up here, correct? Second, the batch gradient descent path actually stops at minimum, while the stochastic and mini continue to roam around, right? The basic gradient descent takes a lot of time to take each steps, right? That is another thing. While batch gradient descent takes a lot of time, both stochastic and mini batch reach the minimum. Basically, the batch gradient descent takes a lot of time, while both SGD and mini batch also can can reach the minimum provided good learning schedule. Okay, so that's important part. All right. So here is a very important table for all of you, right? So there are multiple algorithms so far we have talked about, right? And first one was normal equation. Remember normal equation whereby we differentiated and equated at zero. Second was the batch gradient descent. Third is the stochastic gradient descent, and fourth is the mini batch stochastic gradient descent, right? So sorry, mini batch gradient descent. So stochastic gradient descent, mini batch, and batch, right? So if the number of instances is high, which one is slow? Quickly, the batch gradient is slow because at every step we are going to compute the the overall error, right? Therefore, this is slow. Out of the code support, meaning can entire computation be done in the memory and not overflow, right? In case of stochastic and mini batch, the answer is yes, because because they don't require too much of memory, correct? While in case of the normal equation, we have to load the entire data into memory. Only then we can do inverse or any kind of dot product or so on, right? So normal equation demands us that, hey, we need entire data in the memory, right? While batch gradient descent also has a similar behavior because it does the calculation on entire data set. And since the way we use the entire data set in our case is using the linear algebra way of doing things. Therefore, I mean, creating a vector, creating a matrix, and then doing that. Therefore, the batch gradient descent also will take up the memory, right? Therefore, normal equation and batch gradient descent will take a lot of memory, and hence not every data can be loaded into the memory, correct? Now, if the number of features are increasing, if number of features are increasing, normal equation is slow while others are fast. The hyperparameter in case of normal equation is nothing because it's just very definitive way of calculating. While in case of batch gradient descent, the number of hyperparameters is 2. In case of stochastic and mini batch, the number of hyperparameters is more than 2. That includes like learning rate and so on, the learning schedule and so on. Okay. Next is
Next is scaling required, as in, do we need to scale our data or not, right? Remember our diagram that in case the data is skewed, one value is varying from 0 to 1 and other value is varying from 0 to 1000. In case of gradient descent, all the three, we need to scale our data, but normal equation does not require you to do the scaling, okay? And the function that you use in case of these methods, there's no equivalent function in scikit-learn for batch and mini batch, right? While for normal equation, we'll just use the linear regression, the class that we have already used, and stochastic gradient descent at the SGD regressor that we just discussed, right? So I hope everybody is clear about these four things that we have learned so far. Yeah, normal equation, batch, stochastic, and mini batch gradient descent. Yes, Alsayed, Arun, Bo, Deepak, Jay, Manoj, Nikita, Prashant, Robert, Satyajit, Sumit. A question from Deepak is for the batch gradient descent and for the mini batch, do we need to write our algorithm? Most probably yes, but I can take a look if there is some alternative. Yes, go ahead, Bo. In case you have any questions, just feel free to ask. It's a good time to ask. All right. So in simple words, if your number of records are too high, number of features are too high, never use normal equation. If your number of instances is too high, never use batch. Okay, either use stochastic or use min batch. All right. Also, there are faster optimizers. Yes, thank you, Robert. Do these facts also apply to deep learning? That's correct. Okay, like for example, it just has to happen that the next slide is about deep learning. So you will see that in case of deep learning, we will again revisit the gradient descent. There are some of the wonderful optimizations that have happened recently. Okay, so here I think 171 slide onwards. So these are the fast optimizers available. We will talk about these again. Okay, these momentum optimization, Nesterov, AdaGrad, RMS prop, ADAM optimization. These are minor tweaks, or you can say optimizations on top of the existing gradient descent. All right. So, so on top of gradient descent, there are other variations such as the different kind of optimizations and so on. And the gradient descent we will be using as a whole even in the deep learning models. Okay, now let's talk about polynomial regression. So far we just talked about linear regression and we were pretty happy, and we just thought, so far we just looked at the data having linear relationship or straight line. What if we have to fit non-linear data like quadratic equation? Right? So in case we have to fit non-linear data like quadratic equation or something which has more non-linearity, in that case we cannot use the standard way of computing gradients and so on, but we could use the polynomial regression. Okay, so quadratic equation is something like this. Here we have a graph of quadratic equation, which is y equals x square minus x minus 2. And clearly, a straight line will never fit this data properly. That's right. So you will not be able to fit a straight line into this data. So how do we fit this kind of nonlinear data? How do we do the prediction on this kind of data, right? We can use a linear model to fit nonlinear data, what we are going to do is we are going to add powers to of each feature as new feature and train a linear model on extended set of features, and this is called polynomial regression. Okay, all we are going to do is we are going to generate a lot of features by applying all kinds of powers, and then let it figure out the model. Okay, let it figure out the model. So let's test. So first we generate some nonlinear data. This is our quadratic equation. We are going to generate the nonlinear data from this by putting some noise. And then we have number of instances 100, and okay, and we are generating capital X and Y using that formula, right? We're generating Y using that formula, while capital X we are generating using random data. All right, and the generated noisy data in terms of X and Y looks like the way it is shown on the screen. So the scikit-learn library provides a class called polynomial features. We can use polynomial feature class to transform the training data and add square of each. So what we can do is we can ask polynomial features class to transform the training data to add square of each features in the training data as a new features. Okay, so new features equals to existing features, whatever were there, plus square of each features in the training set. So this is an example of creating more features. So we use the standard same methods, linear methods, just that we increase the number of features by squaring the data and so on, right? Right? So this is how we solve the nonlinear problems with linear models. So here the model would remain linear, just that we are including more features which are nonlinear, right? If we say degree equals 10, then it'll be the total powers will be up to 10. So here we are basically squaring all the columns, and actually there is only a single column, therefore there is going to be one more column after squaring it. That's correct, Deepak. That's correct. That if I mean there are 5 features and then we are squaring it, there will be 10 features. Actually, there will be more than that. I'll talk about that in a moment. The number of features are going to be more than that. Okay. A question from Robert is, don't we risk overfitting? Um, we don't risk overfitting because it's generating a new feature instead of new row. Okay. Good question. Very good question. Question is, do we risk overfitting or underfitting when we are adding more columns? Answer is we risk actually underfitting when there are more columns. All right. Okay. Had we been replicating the rows just like that, then we could have been overfitting. All right. Now moving ahead. So this is the way we can generate more features and so on. And when we do the prediction using this, we are going to get two values. Okay. We're going to get two values. This is you can see that X poly has got 2 columns, which is, you can see 0.75 square, 0.75 is 0.56. So that's the way. Let me just show you in there. All right, so first of all, we generated data, then we basically imported polynomial features. Okay, and you can see that after this, capital X, and you can see 10 records of capital X and 10 records of capital X underscore poly. So it had generated more features using that. Okay, and here we have set degree equals 3. So it has generated 3 columns. You can see this is the square, this is the cube, right? Okay. All right. Once we have generated this new set of features, then we can use the normal linear regression. We can use normal linear regression. So even in case of non-linear regression, we are using linear regression models. Correct? Now moving ahead. So here this was linear regression model, and all right. Now, if you have, say, n number of columns, and you are introducing the features with degree d, would you believe that how many features you will get? You'll get n plus d factorial divided by d factorial n factorial. Okay? So it transforms an array containing n features into an array containing n plus d factorial divided by this. Okay, it's basically saying that, I mean, it's essentially, okay, I'll describe why it is so. Okay, that I think this will give you a good picture. Okay, so all right, let's say that you have two columns, A and B, right? A and B, okay? And you introduce, say, square, a degree equals to 2, okay? Degree equals to 2. So you will, in the end, will get A square, B square, right? And AB, okay? So how many columns? 1, 2, 3, 4, 5. Total 5 columns, correct? If the degree is 2. So n was how much? N was 2, degree is 2. So n plus d is how much? 4. Now it says 4 factorial divided by 2 factorial and 2 factorial. Number of columns is 2, and all right, I think it'll be okay. I think it'll be this. It's going to be 4 into 3 into 2 divided by 4. So it's 6 actually. 6 columns as per this. I think there'll be some other column here, maybe constant or something. So all right. So basically all permutations of so A, B, A square, B, AB, and maybe some constant is generating. All right. So essentially it generates all possible permutations and so on. right? So polynomial regression is capable of finding a relationship between features which linear regression models cannot do. This is because polynomial features add all combinations of features up to the given degree. All right. So if you have a and b and your degree is 3, you will get a cube, b cube. Okay, so in this our case, if we had degree equals to 3, if degree equals to 3, so we'll have a cube, b cube, a square b, b square a, and so on, right? That's what we have described here. So you'll get all permutations. Okay, so once we have done that, once we have generated so many columns, we can happily just call whatever functions we have used so far, whatever models we have used for so far. Correct? Now moving back here. Right? So you can see that here it's able to predict the values correctly. All right. All right. So this is the linear regression model, which we have y equals this and 0.5x, 0.56 x1 squared plus 0.93 x1 plus 1.78, right? Okay, so this is how it looks like. And that's pretty much. All right. So what did we learn? All we learned was that we use, in case we have complex equation, all we do is try with polynomial regression. We may not know how many degrees till we go. Okay, so we'll just have approximation here that becomes a hyperparameter, and then all we do is we keep on introducing features using polynomial regression, and then use the same model what we've learned so far for linear models. Okay, so linear models are the ones that are used to even predict in non-linear way. All right. So this is how it was able to do that. Now, the next important thing to understand when we are training models is learning curve. Any questions so far? No questions? I'll say it, Arun, Bo, Jay, Manoj, Nikita, Prashant, Robert, Satyajit, and Sumit. No questions? All right. So, all right. What we just did was we basically tried to fit the data um, in a parabola kind of like the nonlinear data. So it worked well. And now let's take a look at the plane linear regression, second degree polynomial regression, and 300 degree, and see the outcome. You see that same data, the one that was for parabola, the curve. So the same data when we are trying to fit with linear regression with the 2 degrees and with 300 degrees, this is how it comes out to be, right? So what you see here is this. Please pay attention here. So here, this line that you see is with one polynomial feature, the usual one, meaning the linear regression. This is the linear regression, right? And this one that you see here, this one is the crazy graph. You can see it has gone crazy here. This is 300 degrees one. This is 300 degrees one, which has tried to kind of take it through every kind of dot. Okay, that is 300 degrees. 300 is really huge degrees, by the way. And The 2 here, this one is basically this, you see, 2 degrees of features. Okay, so you can see very clearly that here the best one is the 2, right? Best one is the 2, neither 1 nor 300. So you can see that this one is plain linear regression, this one is second degree polynomial regression, and this one is, you see, this one is 300-degree polynomial regression. Okay, so what did we learn from this? What did we learn from this? Any observations, anybody? As the degrees are increasing, what's happening is the bias is going down, but but memorization has started, right? When the line was straight, it was too biased because it was neither fitting training data nor it was fitting the testing data, correct? As we increase degree by 1, now bias has gone down, as well as the prediction have become very nice, right? But the moment the polynomial regression kicks in with 300 degrees, it has started memorizing, meaning it has become, it has started overfitting, it has become overfitted, right? So as we can see in the previous diagram, 300-degree polynomial model wiggles around as close as possible to every data point. Okay, and it's clear that high degree polynomial regression, this model is going to overfit the training data. The linear model is underfitting the training data. Sure. We're going to talk about that one. Yeah. All right. So what's happening here is that here in this diagram, this 300-degree polynomial, it's trying to go through every data point. And we know for sure that this is just the noise. Actual data is actually curve, correct? So this 300-degree polynomial that you see is trying to memorize everything. It's not letting go of any data point, right? So this one might work great in the testing data, in the training data, because that's what is available to us, right? But in case of testing data, it is going to fail pathetically, because the testing data will also have similar noise and will also have similar random number. Okay, so therefore this trying to memorize the noise is basically that overfitting, or we call that variance, while trying to fit a straight line into a curve is called underfitting. That's what is underfitting, and an underfitting line does not give great outcome, give great outcome even on the training data. All right, so Bo, did I make sense? So on one hand is bias, like straight line is heavily biased, while on the other side is the variance, or you can say overfitting. So question from Bo is that for us, question from Bo is that, so 300-degree polynomial has low model bias but high sample variance. That's right. It is heavily under overfitting, while the straight line is underfitting. Okay. So it has started memorizing. It has started kind of memorizing, and it's going through every data point which it was not supposed to go, right? So what do we do in these cases? A number of times what happens is this. Okay, a number of times lots of models start overfitting. They are doing very good when it comes to training data, but on the test data they flunk badly. So if the data is not, if the training model is very simple like a straight line, okay, let me go back again. So here the important part that we are trying to show is that we know that the data has been generated randomly by augmenting the underlying curve, correct? All we did was we created an equation for curve and then we added a noise, and that's how the data is generated, right? So this data, if somebody tries to memorize each and every data point, they will be memorizing the randomness, right? They'll be fooled by the randomness. And that's what is happening with a 300-degree polynomial. It's trying to kind of memorize even the ones that is entirely random, right? So this is called overfitting. So we went from underfitting till overfitting. We went from underfitting till overfitting. Now, it was easy to go from underfitting to overfitting, but we just increased the number of features, right? We just increased the number of polynomial features. So it was easy to go from underfitting to overfitting, but now when we reached the overfitting, when we got into complex model, we got complex problems. Now, how do we tackle that? This is exactly where where the next point comes in. So when the model starts to overfit, meaning it's doing pretty well on the data it has seen, but really bad on the data it has not seen. In that case, we say that model is overfitting. And how do we handle that? Anybody? It's a very standard question. Not handle. Okay, the question is different. Question is, how do we find if the model is overfitting or underfitting the training data? Quickly, anybody? I just said a minute ago. Question is, I thought you would find the model that has the lowest test data RMSE. Yes, basically there we use the cross validation. And what happens in cross validation? We run the one model. We create, say, 10 instances of the same model, right? And every 10 times we break the data into testing and train automatically, and test it on the 10% of the data 10 times. Okay, this 10% of data that is being tested every time is basically different every time. Okay, and the model is initialized again and again every 10 times so that it does not overfit. Okay, so this is called cross validation. So cross validation is what we use in order to see if our model is doing good or bad. Test data, comparing against test data, we want to keep it for later. All right, so not performing on test data, performing on training data. Yes, that's right, Deepak, thank you. Based on biasing, yes. We use RMSE, yes. We use RMSE in case of regression. We will also learn what do we use in case of the classification. Similar to RMSE, we use something else. We had used what? We had used earlier the accuracy, but we'll have to learn how to convert the classification into regression and so on. Okay. Now a question for Deepak is that yes, in case the mean error is high, it's underfitting. Yes. So we'll have to basically um, do this, that we will have to compare the performance of the model on training and test both. If it's doing bad on both, then that means it's underfitting. If it's doing good on training data but bad on testing data, then it is overfitting. Okay. All right. A question from Bo is entropy for classification. Yes, that's right. Cross entropy actually. Okay. So we'll be using cross entropy for classification, and we'll learn that part very soon. So one approach is to use cross validation and find out if the model performs well on the training data and so on. So this is what we just discussed. We will continue from here. And what we are going to learn next after this is, in case your model starts overfitting, what are the things we are going to do? That's the term called regularization. We will use regularization to bring down overfitting, and that's what we're going to discuss tomorrow at the same time. All right. And then we'll discuss regulation techniques and why do we do those. And then we'll discuss the cross entropy and those parts which convert a classification problem into regression problem. All right. Great. Great. I look forward to see you. Bye bye. Have a good day.